Have you ever really thought about how a simple thread can be stronger than steel? I mean, it sounds kind of crazy, right? Well, today we're going to go on a deep dive, a microscopic investigation to uncover the secret blueprint that makes it all possible. Let's get into it. I mean, really think about that. A thread stronger than steel. It just doesn't seem possible, does it? But the answer isn't magic. It's all about the science. The secret is hidden away at a scale we can't even see with our own eyes, down in the invisible architecture of molecules. So the big question is, how do you actually build a superfiber? Well, like any good construction project, you have to start with the blueprint. Let's break down the absolute non-negotiable rules for creating that incredible strength right at the molecular level. And you know what's wild? The blueprint is actually pretty simple when you break it down. First, you need long, straight polymer chains. Then, those chains have to be perfectly parallel to each other, all lined up. Third, you need some kind of attraction between them, a force holding them all together. And finally, and this is key, you need to allow for just a little bit of molecular movement so the fiber can stretch instead of just snapping. That's it. That's the ideal design. Okay, so we've got the blueprint. That's great. But it leads to the next obvious question, right? How in the world can we see something that small? I mean, how can we check our work and make sure the fiber we made actually follows all four of those rules? We're going to need some pretty special tools to peer into that tiny world of molecules.
And luckily for us, scientists have an incredible toolkit for exactly this purpose. Seriously, you can think of it like a high-tech forensic lab, but for materials. These tools let us see the invisible and understand exactly what's going on with a fiber, from the inside out.
So here it is, the investigator's toolkit. We've got X-ray diffraction, infrared absorption, microscopy, the whole shebang. For our little investigation today, though, we're going to focus on two of the real heavy hitters, X-ray diffraction and infrared absorption. And here's why. Each one reveals a totally different, but equally crucial, secret about where a fiber gets its power. All right, first up, let's grab our X-ray diffraction tool. This one is all about the physical structure. It's basically how we find out if those molecular chains we talked about are all neat and orderly, or if they're just a big tangled mess.
And this diagram really shows you how it works. It's actually pretty clever. You fire a beam of X-rays at the fiber. Now, when that beam hits a part where the atoms are arranged in these perfect, orderly layers, what scientists call a crystalline region, the X-rays bounce off at a very specific angle. By measuring those reflections, we can literally measure the fiber's internal order. And this is the magic formula that lets us decode everything. It's called Bragg's law, and you can think of it as our molecular ruler. It's what lets us translate the angle of that reflected X-ray into the actual physical distance between the layers of atoms. It's how we measure the fiber's structure with just incredible precision. So here's the key takeaway for X-rays. They absolutely love order. They only give us information about the tidy, well-organized, crystalline parts of the fiber, and that's super important for strength. But that's only half the story. What about the actual chemistry going on in there? Well, for that, we need to pull out our second tool. If X-rays are the architect checking the physical structure, then infrared absorption is the chemist. This tool gives us a unique chemical fingerprint of the fiber. Just take a look at this. This right here is the infrared spectrum for nylon, and every single one of those peaks and valleys is a clue. Here's how it works. You shine infrared light through the fiber, and you just measure which frequencies get absorbed. See, different chemical bonds vibrate at different frequencies, and when the light hits them, they soak it up. It's a way to tell exactly what chemical bonds are inside. So let's play detective and decode this fingerprint. You see that peak right there at 1640? Bam! That's the signature of a carbon-oxygen bond. And what about these two over here around 2900? Those are carbon-hydrogen bonds. And that really sharp one way up at 3305? That's a nitrogen-hydrogen bond. It's amazing, right? We are literally reading the fiber's chemical makeup bond by bond. Okay, so let's put our two main tools side by side for a second. On one hand, you've got X-rays, which show us the physical structure, but only of the neat, tidy crystalline parts. On the other hand, you've got infrared, which reveals the chemical identity of everything in there, both the orderly and the messy bits. You put them together, and suddenly you have the complete picture of the fiber's internal architecture. All right, this is where it all comes together. This is the big payoff. We have the blueprint. We have the tools to read it. Now let's connect all those microscopic clues to the real-world properties we can actually see and feel. And here it is. This is the big reveal, the real aha moment. This table lays it all out. The more orderly and parallel those chains are, the stuff our X-rays measure, the higher the fiber's tensile strength. But there's a trade-off. It gets less stretchy, so stronger but also more brittle. And check this out. The more of those polar groups our infrared tool sees, and those are just parts of molecules with a slight electrical charge, the more moisture the fiber can absorb. It's a perfect cause and effect relationship. So when you boil it all down, here's the most important thing to remember. A fiber's properties are not an accident. Not at all. The strength, the stretch, the way it feels, it is all a direct result of that invisible molecular blueprint. And the coolest part? By learning how to read that blueprint, we can start to engineer materials with exactly the properties we want. So, in a way, we've cracked the code. We can now look at a material, read its molecular blueprint, and understand exactly why it behaves the way it does. The only limit really is our imagination. So that leaves us with one big exciting question. Now that we can read the blueprint, what are we going to build next?